And now we're going to go into a little bit more detail of BitTorrent ideas. We'll highlight 3 ideas that's used by BitTorrent to enable the kind of scalability that it enjoys. So out of the 3 ideas, the first one we'll start with is the idea of smaller granularity. This in turn gives us more flexibility in resource allocation. Okay. In this case, the resource is the content and the upload capacities shared by each peer. Now, what is the granularity? Now, instead of looking at the whole file to be shared as a single unit, we'll look at chunks. These chunks could be, say, 256 kilobytes. Now, that is a very small number compared to, let's say, 100 megabyte or even multiple of gigabytes of file size. And then each chunk can traverse a different multicast tree. Okay, each chunk can go down a different multicast tree. And what's the advantage of doing that? Well, first of all, as we will see in the next module, that employing multiple trees to support the same multicast session is a very smart idea. Multicasting here refers to one source and destination. Multiple trees here refers to the fact that different parts of this file being multicast can go down different trees. Now we can compare this to packet switching 2 lectures ago. As we went from circuit to packet switching, we use a smaller unit of granularity called a packet, and each packet can go down possibly different path, and this lead to one of the 2 advantages of scalability or efficiency of resource usage in the internet. And now it is not a packet but a chunk of the file, and it goes down not just multiple paths but multiple trees. Okay, so one tree could be like this, another tree could be like this. Okay. And it turns out that actually going down multiple trees, perhaps because the rich features of the topology called a tree actually is easier to handle and manage than going down multiple paths as well. And this provides basically what we call a spatial pipeline. What's a pipeline? It's like if you know you're going to wash something and dry something, and then you can first put one pile in the washer, and then once done put it in the dryer while the washer is used for the second pile. That is called temporal pipelining, scheduling different components of an overall job. And now we can do spatial pipeline because some packets will traverse this tree, some chunks will traverse this tree, some other chunks go through another tree. This enhances the overall efficiency. It's a smart idea number 1. The smart idea number 2 is that in the old days, when we talk about distributing a file, we say there is a server and there are many clients. And the server will distribute this file to the different clients. Okay. But now when we say there is a peer, is it a server or is it a client? It's actually both. Right. It's both the source and the destination. It's the destination in order to receive the rest of the file. Is also a source because whatever it possesses, it can share with the rest of the network with the other peers. So a peer is both a source and a destination. So we can have those that are just sources like servers, those that are only destinations like clients, and those that are both like peers. Also those that are neither, actually, routers. Okay, they just relay information. All right, so now I have to think about how do I share different chunks. For example, if one pair says I got chunks 1, 2, 3, another says I got chunk 2, 3, 4, another says I got chunk 1, 2, 4, and then I say I got chunk 2, 3, 5. Okay, when they exchange this information, this is called a bitmap exchange. That we realize that, hey, we all want to collect, let's say, chunks 1, 2, 3, 4, 5. So there are only 4 chunks to constitute this small file. Right, so that's multicast. We all want the whole file. We all want, therefore, chunks 1 to 5. But chunk 5 is the rarest. Only one peer has this chunk, whereas chunks 1, 2, 3, 4 have 2 or 3 different peers possessing it. So when we exchange the chunks, let's start with the rarest one. This is the idea of rarest chunk first. It tries to equalize the popularity or availability of different chunks across different peers. And clearly that's a good idea, so that it won't happen that all the peers got 1, 2, 3, 4 and everybody is waiting for this rare chunk 5. And also, just in case this peer got all the files and decide to leave the system, the other peers will still have an available chunk number 5. So that's smart idea number 2, rarest chunk first. Smart idea 3 behind the design of BitTorrent is perhaps the one that most people talk about. It's about the peering construction. Not only it matters what chunks you use, it matters also which neighbors you choose as peers. So again, remember that there is an underlay network, which is the actual physical IP connection network. Above that, there's one overlay, okay, overlay 1. That is the set of neighbors who possess some part of the relevant files, and the tracker tells a new peer, hey, here are your possible neighbors. And then on top of that is another layer of overlay 2, which are the actual peers. This overlay network changes over time, but not that dynamically. This underlay changes very slowly. The time scale of sharing a file pretty much remains static. But this top layer, the second layer of overlay network, changes very dynamically. Okay. These peers can change from one time slot to another. So the question is, how can I select a subset of my neighbors, okay, told by the tracker to me, and call those my actual peers and start sharing files chunks with them? So how do I go from a list of neighbors to peering relationships? As you might remember, we talked about 1999 and 2000, Kazaa and Nutella, and those first generation P2P network had this free rider problem. That is, everybody would like to get content from others, okay, get content from others, but they may not want to contribute either their content or their ability to share the content, which is the upload capacity. Okay, they may want to use upload capacity for other purposes. So how do I solve this free rider problem? We have to provide some kind of incentives. And this may remind you of the kind of incentives we talked about back in lecture 11 and 12 for internet pricing, and back in lecture, say, 2 for auction. So the kind of incentives that can be provided could be, say, tit-for-tat. That is, I'm going to pick 5 peers out of the list of neighbors at each time slot. And 4 out of the 5 peers will be picked by looking at the top 4 peers who have contributed content to me. Okay, so the top 4 that provided content to me with the fastest upload capacity, that will be the list of 5 peers I choose. So if you don't contribute your upload capacity to others, then soon no one will want to be your peer, and you will get no help from others either. Okay. What about the remaining one? Well, that actually goes back to randomization. This is, I guess, the third time we've seen randomization, because a lot of the design in the network requires algorithms acting on things that you don't quite know exactly. In this case, you also don't quite know exactly what is the optimal configuration. In the advanced material, we will talk about a very difficult optimization problem, by far the most difficult one in this course, on pairing relationship optimization. But that requires some centralized control and global view. Short of that, you really don't have an idea about the globally optimal configuration. So what can you do to prevent yourself from getting stuck into an undesirable configuration space? One possibility is randomization. It also helps with unfairness to those who actually have little to contribute to start out with. They simply may not have the right content, or their upload capacity is very small. In the traditional design of the internet, the upload capacity from the clients, the end user devices, is much smaller than the download capacity. Because back then, like 5, 10, 15 years ago, people thought that, hey, why would you need so much upload capacity? Okay, you are mostly consuming content from servers somewhere in the internet, web, email servers, video servers, and so on. But of course, in the age of YouTube and user-generated content, upload is becoming increasingly an issue. And indeed, for P2P, it's often the bottleneck. So maybe you just don't have enough upload capacity, and therefore a little randomization will give you a lift. So the remaining 1 out of the 5 pairs at each time slot will be just randomly chosen. And this is similar to lecture 3 when we talk about randomization in Google's ranking of web pages. The page rank has, say, 15% randomization going on. This is basically 20% randomization, 1 out of 5. So tit-for-tat together with randomization in peer selection is the powerful idea number 3 in BitTorrent. Now, there are many other engineering details, but they don't concern us in this lecture. Now, we can summarize the essential steps in a BitTorrent operation. Let's say a new peer A arrives, and then it will contact the web server and receive a .torrent file, which contains the IP address and the port number of another server, the tracker. So it registers with the tracker of make sure that the tracker knows its existence, update this database saying that, hey, peer number A is here alive. In return, you also receive a list of neighbors, possible peers. Then using some mechanism, you're going to select, say, 5 peers, possibly 4 tit-for-tat, and then 1 randomization. And then you can start exchanging bitmaps directly with these peers and then indicate the availability of chunks of content. Then based on, say, Rarest chunk first policy, you select the chunk, and finally you start sharing the content on the data plane. Now, so far we have not talked about the quantitative side, all these are qualitative description of scaling property. We keep saying that, hey, if you are smart enough, P2P law says, unlike Metcalfe's law, you can maintain a constant number of neighbors, and yet the overall system can scale very well. How do we quantify this self-scaling property, the most important property in P2P networks? So we're going to do a little back of envelope and then a simple numerical example in some ideal situation to illustrate those points, leaving the full-scale version to the advanced material.